And today I will do more math than usual. So I will use my paper notebook, which you should be able to see now. Okay, so limits of sequences is the topic, and it's the first test if you can read what I'm writing. And I want to first repeat the definition and then solve an easy example together. So, well, what is the relevant definition? It is that some sequence A has a limit L. And first thing we should do is look what the types of all the involved identifiers are here. So maybe you want to say something to that. So maybe let's start with A. So what is the type of A? I actually guess most of you, whatever the function has for input type. Yeah, so I'm not sure I understand. So maybe I should put this one in backticks. So A is supposed to be a sequence. So in math, people typically write something like this. And here, our lecture, or in a functional programming language, maybe, or in type theory, we can write it like this with some special notation to make it look more like math. And the special notation is for the application. So we can write AN for the application of A to N. Okay, so this should be read as the sequence A has the limit L. So what's the type of L? Yeah, thanks for answering. Yeah, right. So L should be a real number. And this whole thing is a first order logic proposition. And what does it look like? I would say I just remind you of the definition, and then we can try to parse it together. So it says for all real numbers epsilon, which are greater than 0, there exists a capital N natural number such that for all natural numbers little n, which are bigger or equal n, well, it has to hold the value of the sequence at n has to be at most or less than epsilon distance from this limit. So this part talks about an, which is the value of the sequence at index n. And this expression talks about the difference from the limit. And it says the difference, which is here calculated by minus an absolute value. And it says the difference should be smaller than epsilon. And the idea is that epsilon, so this whole thing gets interesting when we make epsilon smaller and smaller. And this thing here says the difference between the values of the sequence and the limit should also get smaller and smaller. So it should become arbitrarily small. There's some discussion. Couldn't we just represent a sequence with a list because of infinite lists and laziness? Yes, we could. That's right. I mean, we could implement some functions as looking up the value in a list. So I think having a function type here is actually the better interface because it's very abstract. But we could choose to implement some sequence by list in Haskell, which is lazy, so it can be infinite. Yeah. Oh, you can't read my handwriting. Sorry for that. Yeah, and thanks for correcting it. Yeah. Okay, good. So I guess if you're not already very used to this, this is quite a mouthful. So take some time to digest, and I want to help you with that. So here's an example. So let's look at an example and try to understand what it says in this case. So I say my sequence A maps a natural number to 1n, to 1 over n. And I also, yeah, maybe let's guess what the limit can be. So what our L should be when we want to show that this sequence has a limit. Yeah, thanks. So L is 0. Okay, so let's try to prove this. And I guess a good first step is, even if it doesn't do much here, is to just plug in our example into the abstract definition here. So let's do that first. So I'll write it out. It's absolutely clear. Yeah, maybe I should put more effort in my letters. Sorry. So the sequence n goes to 1 over n has limit 0 is equal to the following. So here, nothing happens. So I just write it down. Okay, and now with this part, something happens. For now, I just plug in values. So A evaluated at n is just this, 1 over n. And L is 0, so we have minus 0 here. And the proposition is it's smaller than epsilon. So Okay, there's a question here. We are talking about the limit as the argument approaches infinity. If I understand you correctly, then yes. So the argument from the sequence, this n should approach infinity, and we kind of want to know the value of the sequence at infinity, but that's a not okay way, not mathematical way to say it. So we have to say it like this. I mean, before people invented this definition, they actually said something about n really going to infinity, and they also had infinitesimally small quantities, which are smaller than any finite number. And I mean, that's a first order way to do it with the usual use of logic on real numbers. Yeah. So is this equivalent to saying lim as n goes to in of? Okay. Good question. So yes, this is equivalent to saying limit n goes to infinity of 1 over n equals 0. Yes. This is what this means. Okay, good question. Yeah. Okay, so what to do now? Here's an obvious thing to do. We can work on this part. So this 0 is certainly not necessary. Then we know since n is a natural number, this expression will always be positive. So we can forget about the absolute value. So this is logically equivalent as a proposition to 1 over n is smaller than epsilon. I mean, now that's, I would say, sufficiently simplified. We don't know yet what we want to do with it. So let's keep it like this. Okay, so what do we do now? I guess that's the interesting part now, because we have to prove something like this. And do you have a good strategy to get started with proving a first order logic proposition like this? So what can we do? Okay, that's a good idea. Yeah. And yeah. So guess a n that satisfies its constraint. So you should guess this capital N that satisfies this constraint. Okay. Yeah. So we have to prove an existence. That's a good point. We have to prove an existence. So usually, and I guess for the lecture, you can kind of think always, more or less, this means we have to come up with something. We have to prove an existence. We have to come up with something and show that it is the thing that should exist by showing it satisfies these constraints. So exist says we have to come up with something, but there's for all in the front here. So we have to come up with something that depends on epsilon. And another way to say this is we have to produce a function. So, and I think it's kind of a good strategy here. It's not like every for all exists something proof works like this, but for this, for a concrete example like this, it's kind of always like this. So this means we can prove by giving, it's not good grammar, sorry, by giving a function which maps the epsilon to n. And as it was said correctly, of course, this n that we map to should satisfy this condition such that n satisfies our constraints. That was a good word. Okay, what do we mean by constraints? Everything that's coming next. So after the existence statement. Okay, so we have to come up with a function, and capital N, which depends on epsilon. Yeah, I guess I give you a moment to digest what happens, and yeah. And right, I wanted to answer this question. First idea is just proof by induction. Okay, so induction, I guess you mean the induction from the natural numbers. And that's a good thing if you want to prove something for all natural numbers. So in this situation, there is a for all natural numbers here, but it's not on the outside. So our first step shouldn't be induction. And what's inside here, we could in the end prove with induction. So yes, induction is relevant here, but it will be a very easy induction. So yeah, I usually wouldn't go into the detail of how an induction proof works, but we can think about it in the end. Okay, so yeah, what can we do? We need a function that maps an epsilon to some natural number such that for all bigger numbers, this condition is satisfied. So I think a way to make it a tiny bit easier is to manipulate this condition so it looks more like something which is a function in epsilon. So, and we can just do this by swapping these two, which is allowed because it is multiplication with 1 over epsilon and n, and both are positive. So it's an okay way to manipulate inequalities. Okay, so now we kind of see what our capital N has to be. Any ideas already? Yeah, nice. Yeah, exactly. Good ideas. Yeah, so I mean, we have to come up with an N such that, first of all, this capital N, which we come up with, is satisfies this thing. So it should be greater than 1 over epsilon. So a first guess would be make 1 over epsilon a natural number and add 1, something like this, which we had in the chat here. So very good, yes. And then we just have to check, are all bigger natural numbers also satisfying this equation? And the answer here is yes, so we're good. So when we see this, we kind of know what we can do. We can say n, let me just call it n index epsilon, should be, let me write ceiling, the ceiling function like this, and just add 1, because we have a strictly greater, and there could be a corner case where ceiling doesn't do anything. So we have to add 1 for sure. Yeah. Okay. And then if we take bigger natural numbers, this still remains true, which, if we want to be completely formal and do every detail of the proof, which we would prove by induction, for example, if we don't already want to use a lemma that says. Okay, we have a question. What was the idea behind making the function depend on epsilon and not n? Well, the idea is basically comes from the form of our proposition, because it says for all epsilon, there should exist something, which means we should have a way of turning an epsilon into such an n, which means we have a function which maps epsilons to n's. And yeah. Okay, understandable.
What I was wondering was, how does it help that we switched the space or the places between epsilon and n when we had 1 over n is less than epsilon?
Yeah, okay, here, okay, maybe I should comment on this one in another color. So my idea behind doing this was, I mean, in this way, you can kind of read off the function from this part. So but I mean, that's not correct yet because it's not a natural number, but the expression on this kind of says how you can build the function. I mean, here it's all pretty easy, but if expressions get more complicated, it's a good strategy to arrange it in such a way that you have an expression in epsilon which is smaller than an expression in the naturals. Or in the best case, just some natural number n. Okay. Because, I mean, this kind of, this side kind of tells us what this number has to look like. Okay, maybe for a bit of practice, we could just do it with a slightly different example, so can kind of see how the general procedure could go. So maybe let's look at both at once. Slightly different example. Let's say we look at the sequence. Let's do it like this. -1 to the k over n to the k. You can guess the limit again, but I'm afraid it's not very exciting. So k is some fixed natural number. Yes, 0 as well. Thanks. Okay. Oh, if k is larger than 0. That's correct. Whoa, I missed that. Yes, very nice. Yeah, so let's just assume that. If k is 0, something to the 0 gives 1. So it's just 1 over 1, and then the sequence is constantly 1, which means its limit is 1. Which is also not completely obvious, so we could also think about that, but maybe let's just repeat what we did with this example. So let me just write down what happens here. So we want to show the proposition has limit 0, and this is for all epsilon exists, capital N, such that for all little n greater or equal n, the distance from the sequence to the limit, so I plug it in as last time, is smaller epsilon. Okay, so we can, as we did here, we can just repeat what we did. Maybe I'll just go to this point and so that's equivalent way to say this. And how can we simplify a bit more, maybe? So last time here, I just said I can forget about the absolute value because 1 over n is positive. So the same argument doesn't work anymore here. And look a bit at the chat. -1 over k modulo epsilon gleich n over k. Ah, okay. Yeah. Maybe. I don't know. Yes. We should deal with the absolute value first. So can we? Yes, we can. Thanks. So we are allowed to just forget about it. because the absolute value will actually kill this -1 over k. So this can just be -1 or 1, depending on if k is even or odd. So it just makes the whole expression either negative or positive, and the absolute value removes this again. So we can forget about it. It's equivalent to this. Okay, so yeah, let me know if you want a more formal way to prove this. Yeah. Not right, it's just that. So now it looks almost like the last time. And maybe we yes, you could square and take the square root again. That's right. Yeah. Yeah. Wait. It's not so clear how it helps you, because I mean, if you apply squaring and taking the square root in here, then to know that this is an allowed operation, you need to know that this is positive. And on the outside, you can't do it, squaring and taking the square root, because then you actually have to add an absolute value if you do this in general. So the clean way to do this, maybe I should spell it out a bit more. What to do this without messing everything up, maybe like this. So let's just take some new paper and do it on a side note here. So in general, I need to use red. If you have A times B, this is the same as this. So that's what we really use here as something that could be an axiom or a basic lemma about absolute values. To spell it out, we use multiplicativity of the absolute value. So solid dot for times. And then we can continue by just analyzing this thing. And that's something which we can formally prove by induction. Because if we have, let's give it a fresh name, if this is L plus 1, we can use this rule again. And rule for calculating with powers. Oh, sorry, I wrote it wrong. So let's do it above it. So plus 1. We can use this rule again for multiplicativity and take to the L here and times -1 absolute value, which is of course 1. And then we know the whole thing has to be to run out of space here, -1 to the L absolute value. Okay, and then we can recurse or induct on the smaller cases and see that this whole thing is always 1. We can go down to 0 where it's obvious, or even it's obvious starting with 1, I don't know. Yeah, so this is always 1, and that's something we can then use here. This is always 1. Yeah. So, oh, I totally forgot the 1 over here. I'm sorry. Yeah. So that's what we do here, or one way to spell it out completely. How to go from here to here. Yeah, good. Okay, so let's repeat what we did last time. So last time we said we want to find a function now. We want to prove the for all exists, blah, blah, blah. So function which maps an epsilon to this natural number which should exist. And I claimed it's a good idea to write this in a way that you have n freely and epsilon maybe in some expression, which you can then use as a starting point for building our function. Okay, so what can we do? Okay, yes. We know both are positive, so it's, oh, I'm actually just copying, that's not what I wanted. So, okay, can do it like this, yeah, very good. And now, can we also remove the k to have some n without anything else? Logarithm, yeah. You could, but it's actually easier. Yes, so at least I claim that's easier. I mean, in the end, it's the same, but an nth root might be easier to reason about. Right, thanks. So we take the case root, which is okay as a function and totally unproblematic if everything is positive. Yeah, okay, nice, good. So we can just repeat what we did last time and say, yes, we have such an n for all epsilon, because we can just say map. So maybe like this. Let's move it up here. Map epsilon to this. And now we have to make it somewhat bigger again. So we take ceiling again and add 1. Well, I mean, the logical way to say now that this, yes, it's needed again, this +1, because we could land in a corner case and then we were a tiny bit too small with our n here. Okay, so why is this a solution? Maybe let's think about this again. How should I write it down? Yeah, so this gives us an n index epsilon. And now this proposition means we have to prove that all n that are greater or equal than n epsilon satisfies this equation. But we can use, can we get an example? Because I can't think of any in my mind. Wait a minute, I just finished what I said. Interesting, maybe there is none, okay. But yeah, okay, so to see that we are done with this n epsilon, we have to plug our n in here and reason about or prove that all greater equal natural numbers still satisfy this equation. And we have to plug it in. We can use this form. Here's, it's easy to see, is a solution because, well, what do we have to say? This is smaller, strictly smaller than this. Okay. And I mean, that's always true because this part, so the ceiling expression alone, is always greater or equal. And if we add 1, we get the strictly greater. So at this point, we are done. Yeah, maybe we should write it up a bit nicer in the end. But yeah, let's answer the question from the chat. Can we get an example? Yeah, okay, right. So an example where this equals this. So the question is, can it happen that actually case root of 1 over epsilon is equal to its own ceiling? At least that's a question if I understood it correctly. So, I mean, that just means, now it seems obvious. Okay, so I answered the question by reformulating it and making it obvious. Yes, I just have to find some values such that this thing is already a natural number. Okay, how could I do it? I can basically get an arbitrary real number here. So I could choose, yeah, epsilon and k equals 1. Yeah, that's the easy way to do it. Maybe we want a sporty way. I don't know. So, I mean, I can choose 1 over some square or some cube and choose k equals 2 or 3. So can kind of always happen. Yeah. Yeah, and note that the interesting case, I mean, where epsilon is very small, leads to large 1 over epsilon. So That's actually the interesting case where we get big numbers here, which makes sense because for small numbers, epsilon, we have to go close to infinity in our sequence. Yeah, but I guess now it's time for a break. I don't have like a fixed plan for what to talk about after the break, but yeah, so if you have something specific you want to know, then let me know. Otherwise, I would just continue to talk about limits and things like this. Okay, see you in 10 minutes, I would say. So we have a break until 16:15. Okay, see you. So, welcome back. There were two things in the chat. So first, I think someone asked for my solution to the previous weekly exercise. I think it is about the deMorgan exercise and not the other one. I guess, I don't know. But yes, I guess I can briefly talk about this, and after that, the other question for an exercise. So, someone else likes the other one as well. Yes. So then let's see that we have enough time for both things. Here's, I guess, some of my code for the right part of the course. Just have to, okay, let's do it like this. So I hope you can see my Emacs like this. Okay, so the exercise said we should write a function for deMorgan dualization. It's in a part or in a section that suggests we should do it for this prop type. And when I read it, I actually did something very different things from everyone else because I wasn't sitting in the lectures. I interpreted a bit different one. So the first thing I did was construct a proof term for one case of deMorgan duality. And then I guess, no, that's not what the exercise means. And then I took one version of deMorgan dualization and interpreted this via propositions as types, as some Haskell function, and then I implemented that. And I thought maybe it's supposed to be like this, but most of you did something else entirely. And actually, I think you were right, because Patrick also hinted in the lecture somewhere, I guess, that you should use deMorgan to simplify an expression in propositions. And the solutions I most liked did exactly this. So it's a function from prop to prop, and I should better call it simplify, deMorgan simplify. And so it should map a proposition to some other proposition and use deMorgan laws to simplify. But I mean, it's a bit subjective, I would say. So maybe for reference, let's have one deMorgan law here. So yeah, maybe if not on the outside, not A, B, yes, or not A, not B, and in as much as possible. Okay, yeah. Yeah, so I mean, now we could ask ourselves which side of this is more simpler. And I would say there's no obvious clear answer, and we have to kind of pick a convention if we want to do a simplification like this. And our simplification might be described as we push a knot in. So it means here knot is on the outside, and pushing it in means so to say, down in the syntax tree. So we push it inside this call to end. So we use the deMorgan law this way. So let us just write this as one case of our function. So yeah, type checks at least. So we would have a case like this. And of course, we can also use the other law. So we can dualize OR to an end. Okay, yeah, but now one question, is it a good simplification function? I mean, now it matches exactly one kind of proposition, judging from the first two connectives we used. So it's very special now. And it fails for most propositions. So, I mean, you haven't implemented most cases yet. But yeah, so how to continue? I mean, we could start with this list here. There's an implies. So maybe let's think about what we should do with an implies. Let's maybe push this error case down. Maybe I'm not actually doing Haskell here, so no, it should be okay. Yes, it's not A or B, so that's good. Yeah. So an implies is actually an OR. Now I shouldn't forget, at least in classical logic it is. So now I have the same thing on both sides, so that doesn't help, but I can just rewrite it as an OR and then use what we already did to simplify that. Oh, good. Okay, next is a not. Not something else. Okay, I guess if we just say A here or P, we can't do anything with it. So let's say it like this. So what can we do here? I don't know. Maybe let's just continue and see what comes up. Name and con. Okay, so not some name. I guess we just don't do anything here. And if we have some constant C, well, we can apply the not, I guess. So we can say constant not C. It looks pretty good. Okay, any suggestions for other cases? Yes, not A equals A. Why not? Okay. Not A gleich deMorgan simplify A. Very good. Yeah, good idea. So instead of just removing the outer two knots, we can use our simplification again on A. That could we do in other cases as well? Yes. Yes, so let's do it somewhere else. Yes, here's a good place. Here's a good place. Here's a good place. And we could go down in line on both and or. Yes, let's do that. So I guess you mean the following. And AB could be and deMorgan simplify A and deMorgan simplify B. We don't know, or we don't want to simplify just some and or, but there might be still something in A and B that we can simplify. So yes, that's certainly good. Also in the implication case, I don't know. Here we give it to the or simplification, and that already is doing that. Could specialize it a bit more, but yeah, I don't know. For the not implies case, we could simplify to and A not B straight away. Yes, okay, we could do that. But maybe let's do something else. Yeah, it's a good idea. But one important thing we, I guess, should always do. So for one, is this deMorgan simplify now or simplify in general? Good question. I honestly don't know. I mean, if you want to have a good simplify function, you really should know what the result looks like. So in the best case, it's a normal form and you really know what it's doing, then it's good. But yeah, I don't know about other cases. So I mean, we're here more or less just guessing. So I wouldn't say it's a general simplification function. Yeah, it's partly deMorgan simplify at least, so we could rename it, right? Yeah, I mean, I'm two cases missing. Maybe I should write those down because in those two cases, I really want to do nothing, I guess. So constant C, and I just mentioned them all explicitly. Good. Yeah. Is redundant. Good. Thank you, Haskell compiler. Good. Okay. So maybe let's remove that comment. It doesn't have anyone now. And yeah, but maybe we should some simplification function that uses the deMorgan laws. So I guess that's a good title for that. Okay, what we always should do, of course, is test if what we have written is meaningful and works. I mean, a good test for quick check or something like this would be, maybe let's start on 1. Okay, it should do nothing. That's great. 2, and let's just take 5. You don't like my, can I really copy paste it to arrange it? But thank you for your code contribution. Wow. Can I really use it? I don't know. Okay, it's just wrapped around by Emacs. No, it's not. Ah, it's okay. Yeah, okay. No, okay. I did too much. Okay, yeah, no. Okay, good. No. Okay, yeah, I should remove measure here. Sure. Nice, okay, thanks. Yes, so P5, which you don't see now, is actually one that should be simplified. It's a not and. And maybe we should make a bit of a bigger one, like not or P1, P5. So P6 is this, and is it correct? Okay. If we take this and we plug in, okay. So it's an or which we replace by an and. So we have a not here and a not around this one. And we remove these two knots. There should be nothing happening, and we can draw this knot in and so I guess if it's correct or not depends on how your printing function prints. Sorry, I want my own function back, my derived printing function. Check this. Yeah, it's an and on the outside. I forgot to remove this knot. Yeah, nice. So it works right. And I object to printing this proposition expression like this. There should be parentheses around a, not a, plus a. Yeah. Any questions left? So I guess it was not much testing. And if you develop something, what I guess you should do and what I would really do if I didn't already know how it all goes is more testing during development. So this was a bit cut short now. Yeah, but if there are no questions, yeah, no problem. If there are no questions, I would try to have a look at this other exercise someone mentioned about limit points of a set. So I'll switch back to my notebook camera. Okay, so it is about exercise 2.7. So we have limit points of a set. So our set X here is a bit like the sequence we just had. So it's, yeah, basically all the points in our first sequence, 1 over n for any non-zero natural number. So I actually didn't exclude 0, which I should have. And here's an example that shows that 0 is a limit point of this set. And this exercise asks us to show that 0 is the only limit point of X. So I actually didn't do this exercise, so maybe I don't know, but let's just try. So first repeat, what is a limit point? So see in the book, there's a function called limp, which goes from R, so that's the candidate limit point, to the power set of R to propositions. So we have some candidate limit point P and a subset of the reals called X. And here the proposition we build is for all epsilon greater 0, there exists a Q that's the approximation to our limit point now. So that's some point in the set X, which should be arbitrarily close to X, but we are not allowed to use P itself. So otherwise, every point of the set would be a limit point. Exists P such that, oh no, I'm running out of space, but I guess it's still readable. Okay, so such that this distance is smaller than epsilon. I guess if you haven't seen this before, maybe a picture helps. So you have like a set X subset of the reals, which looks more like a line segment in nature, but I mean, you can do the same in the plane. And maybe I shouldn't draw it like this then. Okay, so we have the real line and some subset X. And now the idea of a limit point is, so if this is P here, then you should, so one way to say it would be you should be able to find a sequence of points in X which converges to this point. So that should be equivalent to being a limit point of the set without using the point in question. So, I mean, maybe I should write this down, what I just said. Limit point Px is the same as there exists a sequence of real numbers such that for all natural numbers, an is in X without P, and it should converge to P. A has limit p. So that would be another way to state it. I hope that's understandable. And I mean, one thing we can notice is if we just take some open interval, something like this, any point inside the set, if it's like a connected thing in the reals, if it's just some part of the real line, then any point in the inside will be a limit point of the set. But also, if we have an open interval, the boundary will be limit points. I'll give you some basic examples. And now there's an example in the book, which says if we say X is this set, 1 over n, for n natural number greater 0, we have 0 is a limit point of X. Is true. Okay, and now the exercise asks, please show, if I remember correctly, that 0 is the only limit point of X. So if we have a statement like this, for me, two ways of proving it come to mind. One is we take every possible limit point, that would be every real number. So we take an arbitrary one and try to show that it will be equal to 0. Or we take an arbitrary one and show an arbitrary one, assume it's not equal to 0, and show that it will not be a limit point. Okay, so yeah, that's basically now a guess what will work better. I don't know. Now I guess I try the second one. Okay, so let, what do we call it? P. Let P be a real number and P not equal to 0. Okay, so we want to show goal maybe it doesn't fit here. Let's take a new line. Our goal is not limit point Px. Okay, so next step, I will take the definition of limit point, plug in what we know, and negate it. So let's take this one. I'll just repeat it. Limp Px. That's equal to. Now I'm just writing down the definition. Not for all epsilon greater 0, q in x without p, we have q minus p smaller epsilon. Okay, so I draw it in. For all becomes an exists epsilon. So this kind of asks us for a counterexample epsilon. It's good. So we have to guess something in the end. And now the not hits the exists, which turns into a for all. For all q in x without p. And now we have to negate this, which is easy. We just have to turn this smaller, strictly smaller, into greater equals. Q minus p greater equals epsilon. Okay. Yes. So we have to find an epsilon. It can depend on p. So p is outside. So p is already fixed. We assumed it here above. So this epsilon can depend on p. And what we are really showing is for all p in R with p different from 0 exists epsilon. So we are actually in the same situation as before. So we have to find a function which maps such a p to such an epsilon. And we have a condition here. Should we do something to it? Maybe. So what did we do last time? We had an exists natural number. Yeah, we don't have that here. We have an exist epsilon. So I guess it will be good that it's alone here. So we can directly use this proposition. So we have to come up with an epsilon from a given p. Okay, so let's analyze what can happen here. Maybe I draw a picture of our set. So it happens entirely between 0 and 1, I guess. Let's look again at the definition. It's 1 over n. So it starts with 1 and then gets bigger. So the biggest value is 1 over 1, and then it gets smaller, but stays above 0. So everything is between 0 and 1. So we can try to draw some picture. So this is a zoomed out part of the real line. And we have 0 here, 1 here, and now I draw some points in x. So that's 1 over 1. And we have 1 over 2 here, and we have 1 over 3 here, and 1 over 4, and so on. Yeah, that's what it looks like. And now we have given some p somewhere. So maybe let's say it's here. And what we want to do is we want to find an epsilon such that for all points in Q, this condition is satisfied, which just says Q is further away from P than epsilon. Further away or exactly epsilon, but yeah, we want to satisfy it, so we can just say further away is good. So we want an epsilon such that Q is further away from P than epsilon. So what does it mean as a picture? An epsilon such that all Q, all points in X, are further away than epsilon. Okay, so what I would draw here is we kind of need a neighborhood like this, which includes P, but no other thing from X. And that's something we can always do. So the relevant property of x is that it's discrete. So that's basically saying that we can always do something like this. And math speak is it only consists of isolated points. So points where you can find small neighborhoods such that no other point from the set is contained in that neighborhood. And I mean, here we can do it with points which are outside of x, and we can also do it with points inside of x. So we can find a neighborhood such that no other point in x is included. So maybe a good way to do the exercise would be to make a case distinction for p, if it's in x or not. Yeah. But in any case, we can just calculate what this epsilon should be. So yeah, maybe let's make this case distinction anyway. So if we say p is in x, then we know p equals 1 over k for some k. And our task is now to find an epsilon such that yeah, we basically have a neighborhood like this. So I draw a little picture here. We have k, 1 over k here. And next to it, we have two other 1 over something numbers. And we have to kind of find something maybe in the middle here, some epsilon. And I mean, you can just take half of the difference here. So you can take the difference between these two, 1 over k plus 1 and 1 over k, and half it. So how can we do this? This is 1 over k minus 1 over k plus 1 and halved. So that would be my candidate for epsilon here. No, they are not the same distance away. So this distance will be smaller than this one. So that's also a subtle point. So maybe we calculate both distances. So what can we do here? Maybe we can simplify a bit by multiplying crosswise. Then we have something like this. So, and oh, well, it's 1 over something, so I guess it's good. Yeah, and I mean, if we would have taken the other bound, we get also a k minus 1 here, I guess. Yeah. Okay. Yeah, but yeah, this one is bigger here. So in general, it's a smaller number. Yeah, right. So the other has a bigger difference. It's a smaller difference. Yeah, very good. So we settled that one. And yeah, I mean, we calculated something now, which seems to be a good epsilon for us. But in the end, we have to be able to prove it, of course. I mean, what's a good argument here? Yes, of course. I mean, It's obvious, QED. No, I mean, I want to give you something. Basically, what we just did, that's not very helpful, but we just realized if we had taken this number, then we would get a bigger difference. So instead of calculating our epsilon, we could first pretend to calculate the difference of 1 over k to any other number in X. And what we find out is this is the smallest such difference. So this minimizes differences from 1 over k to other numbers in X. And then we know this is a good epsilon if we halve it, because then we are below the difference to any other point in X, which is exactly what this expression here asks us to do, to find. Yeah, okay, so maybe let's also look at this case if X is, if P is not in X. Okay, yes. We can do it in some way the same. So maybe it's possible to reconcile both cases in the end. Find Q with Q minus P as small as possible. Ah, wait, no, forgot about that. We actually have to use a property of the real numbers now. And that property is for every real number, you can find two fractions, two rationals, such that this number is between them. And because we have a positive, good. We didn't assume that. So, okay, we'll not assume it now. Okay. So it will be in between two rationals as a real number. Ah, no, that's still not the right property. Sorry. Okay. Maybe one quick way to finish this off is we say P is not in X and P is greater 0. So that makes it a bit easier. And then we have to figure out the following. That there is a K such that P is between 1 over K and, yeah, maybe let's say it like this. Okay, yeah, it has a couple of case distinctions. So, okay, we say it is between 1 and 0 because the case 1 we already had. If it's greater than 1, it's easy to find an epsilon because we can just take half of the difference to 1. And that will work because every element of X is between 0 and 1. And if it's smaller than 0, P, we can do the same. We can just take the half the distance to 0. And that will be a good epsilon. And yeah, so we can assume that. And then we know it's in between some of the numbers of our set. And then just take epsilon is the minimum of the differences, the distances, how to say, to these two numbers. And then we have again a working epsilon. Okay, I hope that helped. And well, see you around some other time, unless there are questions. No, doesn't look like it. So I'll upload the recording and yeah, have fun. See you around. Bye-bye.